Hello everyone, welcome to another edition of Math 101. This is the LCM of two numbers. I did this recording earlier, but there was some problem with it, so I wasn't able to upload it. So I'm just going to run through my my whiteboard here, and I'm not going to write much in addition to what you're seeing now, but I will draw your attention to some important things. So here we're talking about LCM of two numbers, and LCM means least common multiple. Least common multiple is like the twin of GCD, and we'll see exactly how it's like a twin in a moment. But the idea is that we need to find the multiples of two numbers, and then we find the common multiples of those two numbers, and then of all the common multiples we find the least. So let's do our friends 12 and 18. In this case, this is method 1. I'm going to find the lists of multiples of my two numbers, and I'm going to find, of those multiples, I'm going to find the common multiples and then the least common multiple. So we'll start with 12. 12 has multiples. 12 times 1 is 12, 12 times 2 is 24, 12 times 3 is 36, and so on. And I've gone up to 12 times 9 here, but I could keep going, clearly. And one quick way to make a list of multiples of 12 is just by skip counting. So I start with 12, and I add 12 each time. So 12 plus 12 is 24. Add 12 again, I get 36. 12 again, I get 48. 12 again, I get 60. And then I keep adding 12, 72, 84, 96, 108, and so on. You can rig a calculator to do that for you. Some calculators have a nice feature where you press 12 plus 12 equals, and then keep hitting the equal sign over and over again, and it'll keep adding 12. Other calculators may require something different. You can look that up in your calculator manual. Or you can just add by hand or in your head. List of multiples of 18 here. Again, just skip counting. So 18 I start with is 18 times 1. 18 times 2 is 36. 18 times 3 is 54. 72, 90, 108. So those are various multiples of 18. I could, again, keep going, but I decided to stop there. And that should be enough for our purposes now. Sometimes you may have to extend these lists, but these lists are pretty good for our purpose today. So I want to find now the common multiples in these lists. So we see 12 is only in one, so it's not a common multiple. 24 is only in one of the lists. But 36 is in both lists, so I've circled 36 because it's in both lists. 48 is not in both. 60 is not in both, but 72 is in both lists, so I circled it again. And 84 isn't, 96 isn't. 108 is in both lists, so I've circled that. So I have common multiples. 36, 72, 108 are the common multiples. Of those common multiples, I take the least. The arrow is pointing to the least. It's the first one in the list. So 36 is the least common multiple. And that's method 1 for calculating the least common multiple. It's not very efficient, but it does give you, it does connect with the meaning of least common multiple. However, I recommend against using this method, especially if your numbers are large. But go ahead and try it for whatever problem you like. It's worth a shot, and it'll at least get you used to the idea, the concept. Okay, so we can do better than this. We can go faster. We can do factorizations if factorizations are available. In our case, 12 is easily factored. I made a factor tree here, so 12 is I factored in 4 times 3. 3 is prime, I circled it. 4 factors into 2 times 2, they're both primes. And so in my factorization, there are 2 2's and 1 3. So 12 is 2 to the power 2 times 3 to the power 1. And that is my factorization of 12. That's what I need. Similarly, a factor tree for 18. You should have seen this before in a previous video, so I'm not going to run through all the details about making the factor tree, but the factorization, the important part is that 18 is 2 to the power 1 times 3 to the power 2. Okay, so I now stack those two factorizations on top of each other. I put the 2's in one column, here's the 2's column, and I put the 3's in the next column, this is the 3's column. And now I can calculate the LCM easily. It's very similar to the way we calculate GCD, so this is one of the ways in which LCM and GCD are twins. They're not identical, but they're certainly fraternal twins. So in LCM, I take the maximum of the number in the first column. So the largest number in the first column is 2 to the power 2. The maximum of the numbers in the second column is 3 to the power 2. And so I'm using both 2 to the power 2, 3 to the power 2. 2 to the power 2 is 4, 3 to the power 2 is 9, 4 times 9 is 36, which agrees with the LCM we got in the previous method. So here again we see that the LCM of 12 and 18 is 36. All right, method 3, we can use the Euclidean algorithm, subtraction version, to calculate the LCM. Now the Euclidean algorithm doesn't itself give the LCM. The Euclidean algorithm gives the GCD, and you should remember this from the GCD lecture. So if I want to calculate the GCD of 12 and 18, I use the subtraction version of Euclidean algorithm. So I'm going to subtract 18 minus 12, that's the larger number minus the smaller number, and I replace the larger number with the difference. So the GCD of 12 and 18 is the same as the GCD of 12 and 6. Again, I take larger number minus smaller number, and I replace the larger number with the difference, and that is 6. Now these two numbers are identical, so I can take a shortcut here. The GCD of two identical numbers is that number. So using the Euclidean algorithm, I've determined that the GCD of 12 and 18 is 6. So this is old news. We know how to do GCD, we learned it already, but what is new is that I have a formula for LCM in terms of GCD, and that is the LCM of two numbers, in this case 12 and 18, is the product of those two numbers, which is a multiple of both 12 and 18, and I have to divide that product by the GCD. So that's why I spent some time calculating the GCD, so I would have that GCD available for when I use this formula. So the LCM of 12 and 18 is 12 times 18 divided by GCD of 12 and 18. So we can calculate 12 times 18 is 216, and the GCD we know from over here is 6, and 216 divided by 6 is 36. So that agrees with the LCM that we've gotten by previous two methods, and in this case it's quite efficient. So the Euclidean algorithm is a very efficient way to calculate the LCM. If you have factor trees available, they're probably the easiest, but if you don't have them available, I would use the Euclidean algorithm method that I just showed you. Okay, now this formula here is a formula that you should note. You should put it into your study sheet for the course, or memorize this formula. Why is it true? Well, here's why. This boxed formula down here is really the same thing, just a little bit rearranged. And we see that it's true because, let's see, 12 times 18 is the product of these two numbers in the top of this array here. And remember, 12 is 2 to the power 2 times 3 to the power 1. 18 is 2 to the power 1 times 3 to the power 2. Okay, so on the bottom here, I have both the the LCM and the GCD. Notice that the LCM is the max of the numbers in the first and the second columns, and the GCD is the minimum of the numbers in the first and the second columns. So here what I've got is 2 to the power 2 times 2 to the power 1 times 3 to the power 1 times 3 to the power 2. That's if I multiply the top two rows of this array here. And if I multiply the bottom two rows of the array, I have 2 to the power 2 times 2 to the power 1 times 3 to the power 2 times 3 to the power 1. Notice that the top and the bottom have the same ingredients. Same ingredients. Their order is different because when I take the maximum, I get the larger one, and when I take the minimum, I get the smaller one. So here, the order is large, small, small, large. Down here, it's large, small, small. But the ingredients are all the same. So when I multiply the top two numbers together, I should have the same product as when I multiply the bottom two numbers together. That is exactly what I'm saying with this statement here, this box statement, which is exactly the same as the box statement in the middle of my lecture here. All right, so that's why that formula is true. You don't need to memorize the proof of that, but I'm just trying to explain that it's actually a fairly easy thing. Even if you don't memorize the proof, you certainly need to know the formula. All right, so method 4 for LCM is very similar to method 4 for GCD. We're going to use the Euclidean algorithm again, but this time the division version of the Euclidean algorithm. It doesn't really save us much time in this case, but sometimes the division version of the Euclidean algorithm can accelerate our process of finding GCD. So in this case, GCD of 12 and 18 is I divide 18 by 12, and it goes in one time. That gives me, let me see, a remainder of 6. So the GCD of 12 and 18, I replace the 18 with its remainder upon division, which is 6. So that has lowered the numbers that I have here. I do it again. I take 12 and I divide by 6. It goes in 2 times. 2 times 6 is 12. The difference between 12 and 12 is 0, so the remainder is 0. So I replace 12, the larger number here, with its remainder upon division. And the GCD of 0 and 6 is 6. So the GCD of 0 and anything is that second thing. So that is the Euclidean algorithm. It didn't save us a lot of time in this case. It doesn't always save us time, but sometimes it can save us an enormous amount of time. Now I just go back to using the same formula. The LCM of two numbers is their product divided by their GCD. So this is exactly the same as the previous page. Product is 216. The GCD was 6, as we determined up here. And so 216 divided by 6 is 36. So that's LCM is 36, and we see that 4 different ways. Doesn't matter which way, you'll always get the same answer by all these methods. It's just the only difference is that one method may be faster than another in a certain problem, or one method may be better than another for helping us to understand. So method 1 is probably never faster than any of the other methods, but it is useful for understanding the meaning of LCM. Okay, so down here I've got an application of the LCM idea, the LCM concept. And I want to talk to you about Mayan calendars. Mayan calendars, there are numerous different Mayan calendars. The Mayans had sophisticated timekeeping, they had different calendars for different purposes. We're going to concentrate on two calendars in particular today. One is the Mayan agricultural calendar, which was 365 days long. That is very similar to our calendar, our Gregorian calendar that we have studied. Our Gregorian calendar is 365 and some extra days long because we put in leap years. Every 4 years or slightly less than 4 years we put in a leap year. The Mayans did not do that. The Mayans always made their calendar 365 days long. That meant that their calendar, their agricultural calendar, would slowly move through the seasons, and they understood that, and it didn't bother them. They coped with that. So they decided against adding leap years. Instead, they just kept a 365-day calendar. Now, there's a second important Mayan calendar, which is only 260 days long. That's a Mayan ceremonial calendar. It is a sequence of ceremonies, and so they would repeat every 260 days. There is speculation about why that number is 260. Nobody actually knows, I don't think. Although maybe some Mayans still know and aren't telling, but I'm not sure. One speculation is that it has to do with transit of the sun between the tropics. It's an astronomical observation, and there are other theories. Anyway, 200. We do know that the calendar is exactly 260 days long. And so what I want to do is to find the LCM of these two numbers. Why am I interested in that? Well, at some point in history, the two calendars started at the same time. And then the short calendar, the 260-day calendar, came to an end. But the 365-day calendar continued, and it came to an end. By then, we've restarted the 260-day calendar. And so you see they're out of sync now. And they stay out of sync for quite a while, but eventually they will get back into sync again. And so what we want to do is to figure out that period of time between the calendars starting in sync and ending in sync. That period of time is an important concept in Mayan timekeeping. It's called the short count. That's in contrast with the long count, which is yet another Mayan calendar. So there's a lot of different calendar systems, very sophisticated. They combine in interesting ways, and it's something that you may want to read about, but today we're just going to concentrate on this particular problem. How long is the short count? So the short count has to be a multiple of 260. That's because these 260-day calendars fit exactly into a short count. The short count also has to be a multiple of 365 because these longer agricultural calendars also fit exactly into the short count. So we know that the short count is a multiple of both 365 and of 260. So that means it's a common multiple of 365 and 260. And furthermore, the short count is the first time that this happens, that the calendars become in sync. After they started in sync, the first time they become in sync again is the first short count. So that altogether is the least common multiple of these two numbers, 365 and 260. So we are going to use method 2 in this case, just because I feel like it. I encourage you to try it with other methods. The multiplication method is not going to be so hot. It'll fill a piece of paper. So maybe don't try that one, or try that one last. Try that one if you've got lots of spare time. But certainly do try other methods for LCM. I am going to do it by method 2 right here, which requires us to find factor trees. So first, factor tree for 365. 365 is divisible by 5, yes. What is the quotient? 365 divided by 5 is 73. So here's the two numbers, 5 and 73. I've circled them because they're both primes. We know that 5 is a prime. We should have memorized that long ago. 73 is a little bit harder, but you can run through what are the possible divisors of 73. Does 2 go into 73? No. Does 3 go into 73? You can test it, no. Does 5 go into 73? You can use our quick divisibility tests to find out these are not the case. Does 7 go into 73? Oops, 73. No, in that case, that one we don't need to do any kind of test really, because 7 times 10 is 70. So 73 is 3 mod 7, which is not 0 mod 7. Anyway, you can do it however you like. You will eventually determine that 7 is not a divisor of 73. And we can stop here because we only need to go up to the square root of 73. The square root of 73 is 8 and something. So we need to check primes up to 8. We've checked 2, 3, 5, and 7. Those are the primes up to 8. So we've done all the trial divisions. We know that 73 is prime. There may be other ways to know that 73 is prime. You may have a list of primes up to 100, say, or whatever. That's fine. Anyway, we circle it because it's prime. So this is the factorization of 365 is 5 times 73. 260 is probably easier. So 260 is 10 times 26. 10 is 2 times 5. 26 is 2 times 13. 13 here. There. So that gave me a very quick factorization of 260. So now I'm going to rewrite those factorizations using my nice notation. 365 is 5 to the power 1 times 73 to the power 1. 260 is 2 to the power 2 times 5 to the power 1 times 13 to the power 1. And the convention is I put the primes in increasing order, 2, 5, 13, and then the correct exponents on them. And now, in order to write this nice and tidy, I'm going to identify all the primes that appear in either of these expressions, and that would be a 2, a 5, a 13, and a 73. They appear in one or the other or both of those two factorizations. And again, just to be tidy about it, I've written them in increasing order. Okay, so now I can rewrite these two expressions. So 365 I'm going to rewrite as 2 to the power 0 times 5 to the power 1 times 13 to the power 1 times 73 to the power 1. All right, so here I've included an extra factor of 2 because both of these expressions need 2, 5, 13, and 73. So 2 to the power 0 times 5 to the power 1 times 13 to the power 0 times 73 to the power 1 is 365. So I've just thrown an extra 2 to the power 0 and a 13 to the power 0. Similarly, 260 already has most of the primes in it, 2 to the power 2, 5 to the power 1, 13 to the power 1. I have to throw in an extra 73 to the power 0. Why do I do that? Just so that these columns are nicely lined up. You don't see nice columns in this first way of expressing the two factorizations. So I introduced some dummies, 2 to the power 0, 13 to the power 0, 73 to the power 0, so that my columns line up very nicely. Okay, now it's straightforward for me to find the LCM. That is 2 to the power 2, the maximum of these two numbers. And then 5 to the power 1 is the maximum of these two numbers. They're both the same, so the maximum is either one of them. Here the maximum of these two is 13 to the power 1, and the maximum of these two is 73 to the power 1. Now I do a little bit of arithmetic. 2 to the power 2 is 4, 5 to the power 1 is 5, 4, 5, 13 to the power 1 is 13, 73 to the power 1 is 73, and I multiply those four numbers together, and I'm going to get this 18,980. 18,980 is the LCM of 260 and 365. That means that this is the short count in days. So that is the Mayan short count calendar, has 18,980 days. Now, last problem here is a little bit an aside. It's not really part of the main topic here, but it's interesting nonetheless. What I want to know is how many years in our years this is. 18,980 days is how many of our years. Just so I get a sense of how long a short count is in a more familiar measuring unit that we use, years. So in order to do that, I'm going to first look at how long a complete cycle in the Gregorian calendar is 400 years. We've talked about this. So I won't go into detail about it right now, but a complete Gregorian cycle is 400 years long. That is 400 times 365 days. Now remember that we add leap years in, so we add about a leap year every 4 years, so in a 400-year cycle there's about 100 leap years. But remember, we've made, since the Gregorian calendar, a minor correction to that. We've reduced it from 100 to 97 leap years. So in the 400 years from 1600 to 1999, 1600 is a leap year, but 1700 is not, 1800 is not, 1900 is not. So those 3 leap years are removed. So that takes the number of leap years down from 100 down to 97. So this is a discussion we've had earlier. You may find that in your notes. You may remember that from earlier. Anyway, just a quick review of that. So in a 400-year cycle, how many days are there? Well, there's this many days plus 97 extra for leap years. The sum total of those two is 146,097 days. So that means in 400 years, I have this many days. And so the length of one Gregorian year is the quotient of those two numbers, and that is 365.2425. So that is one Gregorian year. So remember, off to the side here, I'm going to say one Julian year, and then Julius Caesar calendar. One Julian year is 365.25 days. So you see there's a slight difference between these two. The Julian year is slightly longer than a Gregorian year. Anyway, this is really just splitting hairs, but that's what math's all about. So, I thought this is a kind of an interesting discussion anyway, how long the Gregorian year is. And by the way, one other thing, and I have mentioned this before, but just a reminder, that the solar year, according to astronomy, is 365.2422, and there's more decimal points after that. So you see that the Gregorian year is closer to the actual physical astronomical year than the Julius Caesar. That's why the Gregorian calendar is better. That's why we use the Gregorian calendar despite its complications, because this number is closer to the actual truth. Anyway, what am I doing? Where am I going with all this? Well, 18,980 days, the short count. I want to figure out how many of our years that is. So I take the number of days and I divide by the length of a year in days. And I'm using the exact Gregorian number. And I get this quotient when I type it into my calculator, 51.9655. So that's about 52 years long. So that is the length of a short count calendar, is very close to 52 years. So the short count could be used to pin down a date uniquely in a 52-year cycle. So if you had a baby and the baby was born on day 100 of the ceremonial calendar and day 285 of the agricultural calendar, then you could figure out exactly when in the cycle that baby was born. You could figure out someone's age based on just that information. Actually, those things you would do using a variation of the Chinese remainder theorem that we talked about. But that's a little too much detail for us. Today we're just talking about LCM, so I'm not going to go into detail. I'm just telling you how it was used by the Mayans. So it's a very sophisticated calendar system that used a lot of interesting mathematical ideas. Anyway, that is it for LCM of two numbers. I would have preferred to write everything out, but I had already done that, and for some reason the recording was lost. So I'm doing it over again, just reading out and tapping it out. Anyway, I hope this is a useful recording for you. This is review anyway. I hopefully will get more skillful with my recordings as I practice more. And that is it for today, so stay safe. And I will see you with some more recordings shortly.